Hello, and welcome to another Chemistry with Mr. Faust tutorial video. Today we are going to continue into Module 0, where we're going to start talking about dimensional analysis and conversion factor problems. For our first problem, we're asked how many seconds are in a workday that lasts exactly 8 hours. So in this problem, we are starting with 8 hours as our beginning unit, and we're asked to convert this to seconds. So when we have a problem like this, we're going to rely on conversion factors. And as we've talked about in class, conversion factors are just two numbers that are equal to each other, but they have different units. In this example, I need to find a conversion factor that uses units of hours and helps me work towards my units of seconds. And for this, I know that 1 hour is equal to 60 minutes. Now that doesn't take me all the way to seconds, but it gets me started in that direction. So I'm going to multiply by this conversion factor. And for conversion factors, we can always write them as a fraction. So this could be written as 1 hour over 60 minutes. Or it could be written as 60 minutes over 1 hour. And these read 1 hour per 60 minutes or 60 minutes per 1 hour. And both of those things are true. So I need to use the conversion factor that is going to help me cancel out my hours as a unit and move towards minutes as a unit. And so if I multiply by the conversion factor that has hours on the bottom, then I can have 1 hour is equal to 60 minutes. And my units of hours will now cancel out, and now I'm left with units of minutes. Now I need another conversion factor that's going to help me convert from minutes toward seconds. And I know that in 1 minute, that is equal to 60 seconds. So now I can multiply again by a conversion factor that's going to help me cancel out minutes and be left with seconds. So I need to flip this fraction so that minutes is on the bottom. So I'm going to say 1 minute is equal to 60 seconds. Since I've gotten to units of seconds and every other unit has now canceled out, I know that I've answered the question of how many seconds are in 8 hours. So now when we punch this in the calculator, we get 28,800, and the only unit that we're left with is units of seconds. So our units are seconds. In this problem, it says the directions for an experiment ask each student to measure 1.84 grams of copper wire. The only copper wire available is a spool with a mass of 50 grams. How many students can do the experiment before the copper runs out? So the starting unit that we have here is that we have 50 grams of copper wire. So we're going to start off with 50.0 grams of copper, and then we're going to move towards trying to figure out how many students. So the ultimate goal for us is to figure out how many students. So we're working towards from units of grams towards units of students. And if I read the problem here, this is actually a conversion factor. Each student is going to get 1.84 grams. So that means 1.84 grams equals 1 student. So I can set this conversion factor up like we did in the previous problem so that my units of grams will cancel out. So I can use this conversion factor, and if I put 1.84 grams on the bottom, then my units of grams will cancel out, and that is equal to 1 student. So units of grams cancel out, and I'm left with now units of students, which is what I was trying to get to. So when we solve for this in the calculator, we get 27.2, and the units of students is going to be our units. Now, because students are not something that we can have a fraction of. I would want to report this answer as 27 students could do this experiment before we run out, and we would have just a little bit of copper left over. Here we're asked to express 750 decigrams in units of grams. Now, earlier in this module, we've learned how to convert just simply by sliding the decimal. But if we ever have to go outside of these prefixes from kilo to milli, sliding the decimal can get a little bit complicated, because then we have to start jumping 3 decimal spots for each new prefix. So sometimes conversion factors are an easier way to do this. So we're going to use dimensional analysis conversion factors to convert this time instead of sliding the decimal. So we're starting off with our unit of 750 decigrams. And a conversion factor that I know is deci is 10 times smaller than the unit that it precedes. So a decigram is 10 times smaller than a gram, meaning that it would take 10 decigrams to equal 1 gram. So now I have a conversion factor like we've used in our previous problems. So if I want to multiply this by a fraction that is going to get rid of decigrams, I can put 10 decigrams on the bottom and then 1 gram on top. And I know the conversion factor is set up correctly if we look at this little diagram that we have here, if for the small units, things like deci, I should have a larger value. So for deci, I have 10 decigrams. And for the larger unit, grams, I should have a smaller number, which is 1. And if I have it set up correctly, that will always be the case. So when I multiply by this fraction, 750 times 1 divided by 10, my units of decigrams cancel out, and I'm left with 75 grams as my answer. For this problem, we're asked to find the volume of a pure silver coin that has a mass of 14 grams. And it tells us the density of silver is 10.5 grams per cubic centimeter. So we've solved problems like this before just by using the density equation. Density equals mass over volume. We would just want to rearrange it to solve for volume. But here we can also see that density can be used as a conversion factor. So we want to look at an example solving it this way. The number that we're starting with is 14 grams of silver. So we have 14 grams. And density is actually a conversion factor. What we see here is that there are 10.5 grams of silver equal to every 1 cubic centimeter of silver. So 10.5 grams over centimeters cubed is the same as saying 10.5 grams is equal to 1 cubic centimeter. So now we have a conversion factor that we can use. If we want to multiply by a fraction that helps get rid of grams, I can put the 10.5 grams on the bottom and the 1 cubic centimeter on top. This way my grams cancels, and I have 14 times 1 divided by 10.5, which gives us 1.3, and the only unit that I have left is centimeters cubed. So that is my unit. 14 grams is equal to 1.3 centimeters cubed of silver. In this question, it tells us that the diameter of a sewing needle is 0.073 centimeters, and it wants us to figure out what this is in micrometers. Now, micrometers is right down here, and we notice it's outside of our normal box where we can just slide our decimal to convert. So here, using our metric prefixes as conversion factors might make this simpler. So when we have two conversion factors that we want to convert, sometimes it's easiest to get to our base unit first and then go to the next conversion factor, or the next prefix that we want to convert to. So here we're starting off with 0.073 centimeters, and we want to convert to units of micrometers. Now, since we're starting at centimeters, we can say that for every 100 centimeters, there is 1 meter, because centi is 100 times smaller than a meter. So I can say that for every 100 centimeters, that is equal to 1 meter. So that's the first conversion factor I want to use. I'm going to put centimeters on the bottom so that my units of centimeters will cancel, and my 1 meter goes on the top. Now that I'm at units of meters, I can look at my next conversion factor, which is micro. Micro is 1,000,000 times smaller than a meter. So what we can do here is say that there are 1,000,000 micrometers in 1 meter. So we can write that as 1,000,000, but I can also say that there are 1 times 10 to the 6th micrometers in 1 meter, or that a micrometer is 1 times 10 to the negative 6th meters. So whichever way works easiest for you, you can do it either way. The way I'm going to do this is I'm going to say that there are 1 times 10 to the 6th micrometers in every 1 meter. So I'm going to put my 1 meter on the bottom so that those units will cancel each other. And my 1 times 10 to the 6th micrometers is going to go on top. And again, using our little visual representation here, micrometers are very, very small numbers. So I would need to have a large amount of them to equal 1 meter. So the fact that I have 1 times 10 to the 6th, which is a very large number, makes sense. That's why we don't use the negative 6 in this case. We say 1 times 10 to the 6th because it is a very large number of very small units that equals 1 meter. So now when I punch this in the calculator, 0.073 times 1 divided by 100 times 1 times 10 to the 6th divided by 1, I get 730 micrometers.